This lesson is on growth and decay, the specific variations of exponential functions. Today we're going to talk about growth and decay rates as opposed to growth and decay factors, because a common application of exponential functions is growth or decay as a percent. So let's look at an example to show you what I mean. The value of an investment of $5,000 over T number of years at 5% interest per year is represented by this expression. 5,000 times 1.05 to the power of T. We can see that this is growth because the value of B is greater than 1. We can also see that our initial value is 5,000. Notice the value of the investment at the beginning was $5,000. That's our initial value. So where does the 5% show up? Well, it turns out that since 1.05 is what we call the growth factor, hidden in there is the growth rate of 5%. 5% as a decimal is 0.05. You can divide 5 by 100 to get that decimal. The growth rate tells us what just the increase is, not including the total from last year. So we can look at it this way. We have the initial value. 1 plus 0.05. I think we can all agree that that total is 1.05, right? But when we split it up, it shows us that we're taking 100% of last year's value, the previous value, and then we're adding 5% of that previous value. Let's look at it year by year to understand this. Okay, so at year 0, T is 0, right? If T is 0, remember anything to the power of 0 is 1, which means we get 5,000 times 1, which is just 5,000. Our initial value, right? Initial value is when T is 0. So that's what's happening at the beginning. Then in year 1, T is 1, we have the prior value, 5,000, and we're going to add 5% of 5,000. So that's 0.05 times 5,000, which is $250. We have to add that $250 to the previous value, right? That's the money we made in year 1. So we now have a total value at the end of year 1, $5,250. Now, when we figure 5% next year, year 2, we're not taking 5% of the 5,000 anymore. We don't have 5,000 anymore. We have 5,250. So now we're taking 5% of that. We get $262.50, and now we're adding that to our prior value. So you notice our prior value goes up every year. So our percentage ends up being more money getting added because you're taking a percent of a bigger number. So now for year 3, T is 3, right? So we're taking that $5,512.50. That's the amount we have at the beginning of the year. Now we're going to take 5% of that amount, so 0.05, and multiply it times the $5,512.50. That's going to tell me how much interest we earned in year 3. And then I'll add that to how much money I have. Do the math on that now. Return when you have your answer. So I found 5% of $5,512.50. I got $275.63. I had to round that into cents. And now I add that $275.63 to last year's balance, $55,12.50. And when I do, I get $5,788.13. That's my balance after year 3. So because the growth or decay rate as a percentage kind of hides in that exponential function equation, that y equals a times b to the power of x, it's easier for us to write exponential growth and decay as either y equals a times 1 plus the rate, in parentheses, to the power of x, or y equals a times, in parentheses, 1 minus r. So instead of b, notice you have these parentheses. Instead of b, the growth rate, the growth factor, we're using 1 plus r, 1 plus the rate. The rate is a percentage. And we write it as a decimal. Let's do some examples. I promise it's not that hard. So first, we need to make sure you know how to change between decimals and percents. If we're changing percents to decimals, the result is going to be smaller. So we move the decimal 2 places to the left, if you remember. 7%, we would take that decimal and we'd move it 2 to the left. And when we do it, you fill in any gaps with a 0, and that's where 0.07 comes from. The other way that some of you learned is just dividing by 100. So instead of 7%, you would write 7 divided by 100, and your calculator tells you it's 0.07. It doesn't matter which way you do it, but everybody learned a little differently, and so you can choose which way is easier for you. Now, if you're going in the other direction, decimals to percent, you'll have to do that sometimes, your result's going to be bigger. So 0.23, we either move the decimal 2 places now to the right, which would then be 23%, or we take that 0.23 and now instead of dividing, we're multiplying by 100. Multiplying gives us a bigger number answer, right? 0.23 times 100 is 23%. You have to be able to switch between decimals and percents as needed. Let's look at this example together. We're asked which expression represents the growth of an investment of $8,000. That's going to be our initial value. That's what we're starting with. At 7.5% for a period of T years. When you see a problem like this, you have to read it as, wait, they're giving me initial value and we're growing at a percent rate. That tells me that it's going to be exponential. I'm looking at these 3 choices and I hope you can pick out the one that is not an exponential function. Did you see it? This t is not in the exponent. It is not exponential. That cannot be the answer. So the question now is whether it's this 1.075 for our growth or decay factor or 0.075 for a growth or decay factor. First, they told us it's growth, which means that b is going to be bigger than 1. So it looks like it's going to be this one because b is bigger than 1. But let's check. The growth equation is our initial value times 1 plus r to the power of t. Now r has to be given as a decimal. So if we have the 8,000 in front, we just need to take 7.5% and change it to a decimal. Now I know there's a decimal already there, but remember, percent to a decimal is smaller. You're going to take that decimal and move it 2 places to the left and fill in any gaps with a 0. 0.075. You could also have said 7.5 divided by 100 in your calculator, and you would get this result. All right, when you look at this now, to the power of t, 1 plus 0.075 is, put them together, 1.075. And that absolutely matches this second choice, which is the correct answer. Let's do one more together. So we're given the equation here. Our initial value, remember, is our A. And so I can see that that is 50. Is this growth or decay? Well, I have to look at B, and I see that B is 1.1. B is greater than 1, which tells me that this is growth. What is the growth factor, the value of B? We can see that that is 1.1. The factor is the total of the base. But we have to back out of that to find the growth rate. We know it's growth, but we need the rate, the percentage. Does this equation use 1 plus R or 1 minus R in place of the B? It uses 1 plus R in place of the B, and we know that because it's growth. That's how you decide. Growth uses 1 plus R in place of B. Decay uses 1 minus R in place of B. So now we need to figure out what R is. What is the growth rate as a decimal? Well, 1 plus R is 1.1, isn't it? So what is R? Well, if we subtract 1 from both sides, can't we find R? R is 0.1. Now, what is 0.1 as a percent? Take a minute, figure it out, come on back. All right, 0.1, move the decimal 2 places to the right, and we get 10% growth rate. So when we look at the problem, account B starts with $50 and increases by 10% each year. You see how you can translate the equation into an actual real-world problem. All right, now it's your turn. I want you to try this one on your own. We're going to go over it in class, but it's important that you take the time to try it, be willing to make a mistake. That way we can correct any mistakes and you'll learn from them when we're together in class.